Hey everyone. So yes, I have a consulting company. I call it a boutique consulting company because that sounds way better than small. So we do, various big data projects. I got into it because back in like 2006, I did this code search startup called Krugler, and we were using Nutch, which was a web crawler, and that's where Hadoop came from. So we were using Hadoop back in 2006. And also Solar when it first got open sourced, et cetera. So that was my exposure to big data. Now, since then, we've done a whole bunch of consulting projects. Some of them I'm less proud of than others. Like, for example, we did a project to process the Twitter stream to detect celebrity sightings that fed a website for star-crazed people to stalk their favorite actors and actresses. Okay, so, the shame. But my daughter needed braces. What are you going to do? But I also did a project, Project Durkheim, where we were processing voluntarily provided social media data to try and estimate the suicide risk for military people. Right, and that fed into then the psychiatrists to figure out who they should be worried about. That was a little more socially redeeming than that first project. Let's hold off for a little bit. I did a timing, and it was pretty close to 40 minutes, so I'm going to talk fast and leave time for Q&A at the end, if possible, if that's okay. What's similar about both of those is we did those as batch processing because we had this Hadoop hammer, so everything looked like a batch nail, right? That was, and I realized more and more of what we were dealing with was streaming, so I started getting involved in streaming processing, Storm and Samza and Spark streaming. So yeah, I was playing the field, and then I got interested in Flink, and it really resonated with me. Right, so that's how I kind of got involved in Flink a couple years ago. So the web crawling thing is actually kind of a cover story. What I'm really talking about is some of the more advanced features of Flink that maybe not everybody deals with, but I think are really powerful and very interesting. So for example, AsyncFunctions, that's one of them. Iterations, right? Loops in your workflow. And also kind of helicopter stunts that you can do with state to make it act like a database, even though it's not really a database. So what's the cover story? Can I build a web crawler using Flink? One of the reasons I do this is because I know web crawling really well. So I understand the space. It often pushes the edges of systems. So I'm like, okay, could I implement a web crawler using Flink, but with some requirements, right? Scalability. I hope it's scalable because if Flink scales, it should scale, right? So I should be able to run it on lots of machines. It's a specific kind of web crawler, a focused web crawler, where I don't care about crawling pick some number, 500 billion pages in the web. I only want the million pages or 10 million pages or whatever that are most interesting, right? By some definition of interesting. And I want it to be efficient, which means ABC, always be crawling. Like, if you're not fetching pages, what am I spending my money in Amazon on here? So efficient. And the last thing is simple. Because often when we run web crawls for clients, like, I'm DevOps, right, or I'm Ops. So I don't want the layer cake where, yes, first you install the GCC compiler so you can build some library and you have this big layer. I want something that's Flink and only Flink, because that's going to be really simple for me to run. So web crawling 101, quickly go through sort of what the problem is. And at one level, it's really conceptually simple, right? I've got some starting set of URLs, maybe just one. Maybe one URL, apache.org is the URL, flink.apache.org, right? I'm starting off somewhere. And I feed that into I'm going to call it a database, a URL database, which keeps track of all the URLs I've seen that I know about. So it starts off with like maybe one. And then you take the URL and you got to run it through a robots checker, right? Because there's this robots exclusion protocol where websites can say, here's what you're allowed to crawl, here's what you're not allowed to crawl, here's at what rate. If you're writing a web crawler, you always, always, always honor robots.txt. Don't be one of those people who ignores it. That's bad. So then if it passes the check, great, now I got to fetch it. Right? I got to go out and make an HTTP GET request to get the page. The results of that fetch go into some parser. We use Tika to parse it. I'm a committer on the Tika project at Apache, so I know how to make that do what I need it to do. right, to extract, whatever, text, metadata, pick what you want. And finally, it gets written to some output, right, to a sink in Flink. So it seemed too easy. Like we hooked up this initial thing and we used some components from this Crawler Commons project I'm involved with, which has common Java classes that web crawlers need. A couple days, it was all running. Great, except its performance sucked. The throughput was stinky. I'll call it stinky. Like a couple of pages per second, on a cluster. What? Like that is not the performance that I need here. It's not the beautiful scaling that I want. So what's the problem here? The problem here is massive parallelism, right? When you make an HTTP GET request, the computer is sitting there twiddling its thumbs, waiting for the server to decide it's going to respond to the request, and then the bytes come trickling back, right? And meanwhile, I could be calculating pi to a billion places in the amount of time it takes to get back one web page, right? So the way to deal with that is you need to have like 1,000 active requests per single server, right? 1,000 sort of asynchronous requests that are all sitting there just waiting for the data to come back. That's how you get it, right? But please don't do this thing here. Does my laser, it doesn't really work. Don't call set parallelism 1,000 on this operator, right? Because these tasks that you would get, these 1,000 tasks, even if you had a cluster big enough to run them all in parallel, these tasks are heavyweight, right? They're like running a whole like Java code thing inside the task manager in a thread. That's not how you want this to scale. That doesn't work. So what's the solution to that problem? The solution is async functions. So here's the beauty and curse of open source projects, healthy open source projects like Flink. When we first did this, there were no async functions. In fact, there were no process functions. So we did some crazy map where it's got tickler URLs coming in, ticklers coming in here to trigger stuff that, it's running in the background. And then process functions came out and we're like, oh, we can use timers. That's way better. So we switched to process functions and then async functions were released. And like, okay, no, that's the way to do it. So, we rewrote the code over the course of like 6 months, 3 times, which is great, that it's getting better, but it kind of sucks because you're always like, oh my God, the next version of Flink's coming out and I need to change everything. So what are async functions? On one level, they're pretty simple. Basically, you've got some function like that extends rich async function, where it's got, here's my input type and here's my output type. Input type, I'm calling it a fetch URL, and the output type, I'm calling the generic result, right? That's what's going on here. You hook it up by using this async data stream helper. It's got a .unordered wait static method, and what that does is it creates an async wait operator that's calling the function you give it. Right? And you can give it a couple parameters. So it's an unordered wait because I don't care, like if I tell it fetch page A, page B, page C, I don't care if I get back C first and then B and then A. It doesn't have to come back in the same order that I send it out. If you do an ordered wait, then it has to buffer the results to the point where like things are in order, which we don't need, and it creates latency and inefficiency at times. The other thing is you can give it a timeout, in this case 20 seconds. Like if it gives me something to like fetch, and I haven't fetched it in 20 seconds, it's going to kill the workflow, which we'll talk about why that's a bad thing. And in your rich async function, you've got an async invoke. Like normally with map functions, you got some map call. Here's the input record, and here's what I want coming out. Well, with async invoke, you get this result future. And what that is something where, okay, in the background, async stuff's happening. When you finally get your result, you call complete on it. So you don't call collect like a regular Flink function. You're calling complete on the result. And that's happening, it has to happen async. If you block on the call to async invoke, you've completely defeated the purpose of having this async function. You can't, it's got to immediately like queue something up to be processed asynchronously in the background. Now, obviously, if the thing that's actually doing the work is also like an async client, that makes it easier. In our case, we were using HTTP client that's part of the Apache project, and we're using the non-async version of that. So that means we had to create a thread executor with like thread pool, and we put this thing into the queue, and it gets processed, right? Not horrible, but it's a little bit of extra plumbing. All right, so what about that timeout failure? So the issue here is if it does time out, it's going to kill your workflow. And it doesn't matter what value you use there. Like if you're hitting a web page, there's a web page that would kill your workflow. Like that's one of the things you learn when web crawling is it's an almost infinitely large universe, and so you will hit every edge case that you never considered, right? So you'll try and hit some web server that's actually running in Bob's basement that's trickling data back at 1 byte per minute, and like 3 weeks later, you get your web page that says this site under construction. So you need to make sure that the client you're using has support for timing out. Like that's the right way to do it. And then if you want, you could use the Flink timeout as a total safety net. Like this page should come back in 10 seconds, and if after a minute we still don't have a result from this thing, okay, something's really wrong here. Like, so let's kill the workflow. If you kill the workflow, you get like this kind of stack trace in there, like timeout exception, async function call has timed out, right? Now what's interesting here is when you go back and you look at the setup here, you're not telling Flink, in this case, you're not telling Flink the maximum amount of parallelism, right? You can actually pass another parameter to this unordered wait helper function that says, here's the maximum number of sort of simultaneous asynchronous requests I want. If you don't provide that, it's unbounded, which means then your client better have some bounding on it, which means when it calls async invoke, if you've got like all 1,000 threads busy, then it should block, right? Either one or the other. You either do it inside your code, or you tell Flink what the limit is. All right, so what about back pressure? So this is currently kind of another problem with async functions. The way that Flink gives you that nice back pressure metric in the UI is it's actually watching calls to the collect method and seeing how long they block for. But the problem is with an async function is it's not calling collect, right? It's calling that complete guy, which is actually something in this async IO thread that gets spun up for each one of your different async functions. So you don't see any back pressure, even if there is back pressure. Right? What you wind up doing is, like I had to hook up your kit to figure out what was going on, and I see all these blocked threads. Or you could do, caveman programming with kill minus quit of the task manager process ID, and you get the thread dump in the log, and you look at it and you go, oh, why is it hung there? So that's one issue. No side outputs. So I don't know, has anybody here worked with side outputs in Flink? A couple people, right? So side outputs are actually really cool. Like you can have a Flink operator, and here's its main data path, and then you're like, oh, but you know what? We've got some additional data, and it kind of becomes this side output that you can hook into. So that's cool. That's really useful. For example, with this robots checker thing that we have, and I put in pink the ones that are async functions, right? So here's this robots checker. It needs to fetch the robots.txt file. So that's an async function. I have 3 outputs from it. If it managed to fetch the robots file and it checked the URL and the URL is okay, then I want to pass the URL on to the page fetcher. Like that's the main path. But if the URL gets blocked, I need to now let the rest of the system know that I couldn't fetch this page. So that's a status update. That's a side output. And I also have, like, if I fetch the robots file, inside there could be a link to a sitemap, which is like manna from heaven if you're a web crawler, right? Because that's a list of, like, here's all the really good stuff on this website. And by the way, anybody who's involved with the Flink project, flink.apache.org should have a robots.txt file that says, here's the links to the latest documentation. Because if you had that, then when you go into Google and you search, you won't get like this 1.2 version of the documentation or the 0.9 wiki page. Like you could fix that problem. It would just take one file. Anyway, so sometimes we get sitemaps, like links coming out of the processing of robots, and we want to pass them down a different pipe. So these are side outputs, but we can't do that because it's an async function. So how do we do that? Well, it's this weird thing where our output from the function is actually a tuple3. If you see it up there, can you see that this tuple3 right here? Where it actually has 3 things. When we output one of these tuple3s, only one field is going to have anything in it. The other 2 fields will always be null. And then we can use Flink's support for like selecting from a stream to split that into, oh, it's a status update because only this is filled in, or it's a page that we need to fetch because only this is there, or it must be a sitemap because only that thing's filled in. Right, so that's a way to work around no side outputs. there's also kind of this interesting thing with chaining back pressure. So I don't know, like, people are aware how Flink optimizes things, right? If you have like an operator and another operator after it, and there's no partitioning happening between there, then it's going to try and just sort of pass it on to the very next operator without putting it over the network. Because as soon as you put something out over the network, you got to serialize it, and then you get your network traffic, and things slow down. So chaining is a way to make things more efficient, right? Well, if, in this case, you got an async function that's followed by, let's say, a parser, what'll happen is the async function calls the complete method, which is running as part of this async IO thread, and then that's going to chain, and it's going to pass that on to the page parser, right, as part of this. So what happens in this case, when we first coded this thing up, is I had 1,000 threads running in here, but they were all blocked waiting for the async IO thread to finish taking this output and running it through the parser and then writing it out. So what we needed to do is change the parallelism of this. So we make this higher parallelism, like, this, if I got 2 of these running, I have like 10 of these running. That forces then a partitioning, and also means, we have enough parsers running to sort of keep up with the number of threads we've got, right? Makes sense? It's not really something specific to async functions, but it kind of surprised me. I just assumed an async function wouldn't chain, and it does. Okay, but wait a minute. That's not a web crawler. That's a fetcher, right? I had my initial set of seed URLs coming in here, and I fetched it, right? And I wrote it out, but the status thing wasn't there, right? So that's one of the things I need, like when a URL gets rejected by robots, or if I try and fetch the page and it's not there, so I got a 404 result, I need to update the state of the URL in the database. And the second thing is, this doesn't actually expand, right? I have like, here's my 10 seed URLs, it fetches those, I'm done. That's not a crawler, that's a fetcher, right? So the crawler part comes from the parser extracting links from a page and then feeding those back in as like, hey, here's some potentially new URLs that you can fetch, right? And that's what causes it to be a crawler, to expand this horizon of known URLs constantly. Because in theory, pretty much every page in the entire web should be reachable from some other page. Otherwise, it doesn't get crawled by Google, right? So, but what does that mean? I mean, the problem here is these right here are loops in my workflow, right? So that's where you come up with the need for iterations to the rescue. I could have handled this if I had like Kafka. I could have written output to Kafka, and then into topics, and then those topics are inputs that feed back into my thing. But again, I didn't want any additional infrastructure. I didn't want to have like Kafka or some other queuing system running. So iterations saved me here. So how do you do iterations? Well, I've got some stream like seed URLs up here, and I can call .iterate on it. And I can give it like a timeout value, which we'll talk about what that means. As soon as I do that, I get this iterative stream as the result of calling iterate on it. And then with this like URL DB iteration, I can do a bunch of other things. And eventually, I can come here and I can say close with the final stream, like my initial thing. And that's what creates this loop. When it does that, what it's kind of doing is creating a virtual source and a virtual sink, right? That's these two things right here. You don't see these in your code anywhere, but essentially that's what's here, and they're connected by an in-memory queue, a blocking in-memory queue, right? So Flink is sort of abusing iterations by sort of synthesizing sources and sinks for you, right? And that's what creates the loop. And you can actually have loops and loops outside. Like, it's kind of crazy how free form it is right now, which does create problems, and we'll talk about those. So this timeout is optional. If you don't have a timeout, the iteration never ends unless you kill your workflow, and unless you cancel it. If you do have a timeout there, then what happens is when this thing hasn't received any data for that amount of milliseconds, it pretends to be a bounded source, a source that has run out of data. And Flink, when a source terminates, it starts terminating the workflow. Right? When a source is like done, then it starts shutting things down in the workflow. Remember when I talked about back pressure? So the interesting thing here is you don't actually see this thing like as having, well, you do see this thing as having back pressure when this queue between them gets full, when this thing is backed up trying to feed data into here. That was the one place we saw back pressure with all these asynchronous functions. All right, so now, fun with fan out. So we've got a URL. Let's say it's flowing through the system. We fetch it. We get the page. The page has 100 outlinks on it. We feed those 100 outlinks back up into our crawlDB. Our crawlDB now says, okay, our URLDB now says, okay, well, let's go process those links. And they start flowing through the system. And each one of those could wind up with a page getting fetched and 100 links coming off of it. So you're getting this fan out. And what happens is, eventually, it fills up the network buffers. And when all the network buffers are full, you get gridlock. Because basically, like this function near the top of it is trying to output something to the next operator, and it can't, because that operator's network buffers are full. The reason why is that operator is trying to output data to the next operator, and its buffers are full, because it's trying to output data to the top of your iteration. And that's blocked because of what we just talked about. So you wind up with like Manhattan-style gridlock. Right? And everything just stops mysteriously. And when you don't have accurate back pressure, it's really mysterious when that happens. You're like, what the hell? So how do you deal with that? Well, the way to deal with it is throttling. Right? What we do, and I'm going to explain why this isn't a great solution, is in the URLDB, we keep track of how many URLs are in flight. Because any URL we emit eventually will come back around unless we got a bug, right? Because it'll be like, yes, we tried to fetch this page and it was a 404. Or we tried to fetch this page and it got blocked. Or we were able to fetch the page. So at some point, the URL comes around. So we have a maximum number of in-flight URLs. And if we take that maximum number of in-flight URLs times the maximum number of outlinks we able to extract per page, times the size of each outlink, and we compare it to the size of the network buffer, then we're like, well, okay, we're probably okay, which basically means we set some value and then we run, and it's like, oh, did it lock up? No, okay, let's back it. Maybe we increase it a little bit, or maybe we back it off, right? So it's not a great solution, right? The other problem is it assumes no data skew. So let's say I got a parallelism of 2 running here, right? So I'm keeping track of in-flights both here and here. Well, if the result of parsing this page is sending links to the other database, because the links are partitioned by domain, if there's data skew, then even though I'm like, well, I think we're all okay here because I don't have a lot of data going on, this could be getting totally overloaded. And the results of parsing the pages are going to the other database. So you understand like how that sort of, each one of these processes has its own notion of how many in-flight URLs there are. And if data is crossing between them badly, like if it's skewed, then it's not going to work so well. So it's a rough approximation. We talked about network buffer and the fan-out record size. All right. So then there's another problem with iterations. Checkpointing. So checkpointing only works if the sources are generating data, right? If the upstream sources, and iterations don't count as a source in that context. So that means like when we first set up checkpointing, we were generating, our seed URLs, and then no checkpointing happened because we had a couple seed URLs, they were done. Because once this ended, this iteration had said, well, there's nothing to checkpoint because we got no more data flowing into it from a real source. So what we did is we changed this seed URL source to be a seed and tickler URL source. So it's a floor wax and a dessert topping. So what it's doing is it's, in addition to the URLs, it's saying here's the initial starting set. It also, every 100 milliseconds, outputs a fake URL that flows through the system and keeps checkpointing going. All right, does that make sense? So, and there's another issue where if there's a URL that's in motion here and we want to, I don't know, do a save point or whatever, it's going to get lost because it doesn't know that this URL needs to come back around up to here to have consistent state. Right now, There are two different improvements, Flink improvement proposals, Flip 15, Flip 16, that will solve this problem. I don't know when. When are those supposed to go? Yeah, like you were, Fabian, right there. What? Let's get it on film. Yeah. The interesting thing for us for web crawling is we don't really care. Like, let's say we drop a URL that's going around here, right? So we fetched it and we don't correctly update the state to be fetched. Well, we'll fetch it again when you restart the workflow. Like, so what? Right? So that's another nice thing about web crawling is it's kind of loose, you know? And then there's the question of when are we done? Like normally, as I said, when a source is exhausted, that's when the workflow shuts down, right? And so when you actually cancel a job, it'll basically trigger a cancel to the sources, and the sources stop emitting data. With iterations, like you can give that timeout value that says, oh, there's no new data coming around in whatever, 10 seconds, so let's assume we're done. But it's super fragile because let's say you have a checkpoint happening and the checkpoint lasts 5 minutes because I'm writing really big state up to S3 and Amazon's misbehaving. That can exceed whatever sort of maximum timeout I put in there, and then my workflow shuts down when I really didn't want it to shut down. So we don't actually use that timeout there. What we do is, again, from that special seed and tickler source, when it says it's time to cancel, we emit a special kind of, yet another special kind of record that flows through the system and says, hey, it's time to shut things down, right? So we sort of have to manually implement this. But it's a work in process. It doesn't really work the way I think it should work. So what about checkpoints? So this URL DB here, that's useful state, right? That's all the URLs we found, whether we fetched them or not, you know, what was the result of the fetch. We don't want to lose that state. So we use managed key state, right? There's managed and raw state, and it can be keyed state or it can be operator state. So managed key state, Flink does a lot of the heavy lifting for you, right? If you've got, so for each unique key, whatever you've picked as your key flowing in there, it's got state, and it can be, you know, it's got to be a keyed stream, of course, because otherwise you don't have a key. And it's all these different kinds of state, right? A value state, which is like a single number that's associated with each unique key, or you can have a list, or you can have a map. And this works pretty well. But what if you need something more out of your state? What if you need to treat your state like a database? So why do we need to treat our state like a database? Now we're going to get into focused crawling quickly. So what is focused crawling? There's an assumption, like we only want to crawl some of the web. We don't want to crawl all the web. How do we do that? Well, the first thing is we have some way of scoring a page. Like here's a page, is it about Flink? Give it a score from 0 to 1, right? Once we've scored the page, when we get outlinks off of that, we divide that score up among all the outlinks. Only has one outlink, that outlink gets all the score. If it has 10 outlinks, they each get 1/10 of the score. That outlink, when it comes back into the URL DB, we add its score. If that link is already in there, we add its score to it. Right? If it's not there, okay, create a new entry. But if it already is in there, we add its score in there. And so then, if when it's time to fetch, we can pick the link that has the highest score. That's sort of an estimate of the page score. Because it assumes good pages, for whatever definition of good you got, those point to other good pages. Basically like PageRank. Right? So we just have to pick, all you have to do is pick the highest links and always be like, those are the next ones we fetch, right? The problem with that is that when you do that, like with a batch crawler, like, you know, Nutch, it spends all its time eventually sorting the links that it's got, right? The batch crawlers work in loops, and so what happens at the beginning of each loop is it says, okay, well, let's take all the links we've got, which ones are unfetched or time to fetch, let's sort those based on the score, and then let's pick the top, you know, 100,000 to process this loop. That winds up being like 95% of the time of your workflow is like doing this. So that always be crawling thing gets violated, right? Because we're always interested in just a small subset of them. So what we do is we have a priority queue, right? A queue that's sorted by the scores in memory. And we're constantly like injecting URLs into there and kicking out the lowest scoring ones. And separate from that, we've got something that is pulling the top URL off of it and sending it on to the robots check and the page fetcher. So we sort of have this queue there. So it means that we don't know for sure that we're getting the highest scoring URL each time, but we're getting pretty good URLs every time. And in streaming processing, that should be your goal, right? It's always like approximate. Like maybe I get late data, so my thing I'm calculating isn't completely accurate. That's okay, right? So in a similar vein, we don't know we're getting the absolute best URL, but we're getting good URLs to fetch. But how do we do that, right? The state is not a real database. It's a key value store, and it's keyed off of whatever the key is that's coming in there, right? We want to constantly be iterating over this list of URLs that we've got and trying to stick them into this priority queue if it's time for them to be fetched. We key off of the domain. So we could key off the domain, and here's a list of all the URLs, and every time we get this list, we could go through that list and find the top scoring one. Okay, every time we do that, the entire list gets deserialized. So you could have millions of URLs for one domain. That would not be very efficient. Every time we add something to that list, we'd have to reserialize the list and write it out to the state backend. So there is a solution, and I don't know if it was Fabian or somebody pointed this out on the list, which is pretty cool. If you use a map state, right? So we've got a stream coming in, and there's a stream key. In our case, it's the domain of the URL, right? That's the key. So when we come into the function, because we're using manage key state, what we've got is a map that has every URL that we know about for that domain. And the key that we use is just an incrementing number, 0, 1, 2, 3, 4, 5. And the value is the actual URL. And then we have two other states, value states in here, one of which says, how big is this map? And the other is, where are we in the map currently? So when we come in, we can say, okay, our current index is 2. Let's do a get from the map of value 2, which gives me this URL, right? So I process that URL, and I increment this value. And if it's greater than this, I loop it around to 0. Now, the reason why this works is because under the hood, like in RocksDB, the key that it's using is a combination of the stream key and the map key. It's like a composite key. So when I do a map.get of something, I'm only getting this one entry. I'm not deserializing the whole map, right? So it lets me do an incremental iteration over everything using this approach. So that's kind of an interesting trick. But now we have another issue. I constantly want to be iterating over every URL that I know about in my state, but I only get access to the URLs for a key, right? Back here, the key is like domain.com. I don't get domain2.com when I'm in here processing domain.com. So what I need to do is I need to get regularly called with entries for every known domain. So what's the solution to that? Well, we just add another state upstream called the domain DB, and this keeps track of all the unique domains that it's seen. And when it gets ticklers from the upstream source, it regularly walks through that list and it emits a special kind of a URL that's just the domain tickler that this function here then uses to say, okay, let's go and look at the next URL for that domain. There are other issues. So we're not going to get into other issues with this, but I was doing some helicopter stunts to avoid having like an external database, right? Or writing my own state backend, which I actually started doing. Because this domain DB, it's unkeyed, sort of semi-managed, it's unkeyed operator state. It implements the list checkpointed interface, so it's a pretty simple way to sort of get called to save the state and get called to restore the state. So that wasn't too bad, but it's got some issues. When the stream gets repartitioned, it's storing state that just happens to be for whatever keyed data is coming in here, but that state can get redistributed among the operators, not on that same keyed basis. And that's a more complex topic that we don't have time for right now. All right, so in summary, these state stunts, looking at it now, these state stunts are pretty ugly. I'd actually started writing my own state backend using this approach called the drum map, which is kind of a very efficient way to keep track of URL state. But I got into checkpointing, implementing checkpointing for it, and I was like, oh my God, this, I'm gonna spend all my time doing this and not actually having fun working with Flink. So I'm like, okay, let's try the abuse state approach, which actually worked. Stormcrawler uses Elasticsearch for this. right? So you can put all the URLs in there. You can make a query to Elasticsearch saying, get me the unfetched URLs, filtered, sorted by their score. That works, but now I got this external infrastructure that I have to keep track of. Or maybe at some point, Flink's going to give me better support for directly accessing what's in like RocksDB. Because RocksDB is more like a database. It's just what's exposed in the state interface is pretty limited. Iterations work. And before I go into this, I mean, iterations are really powerful for things like machine learning, right? Where you like have something that you need to iterate on to like build the model. So it's not just this kind of weird case I'm talking about here. Iterations in general can be very powerful. But, like that tickler approach to keep the iteration running, it feels kind of weird. Again, though, flip 15 and 16, when they happen, will make things much better. And async functions are great. I mean, in my experience, very often you wind up wanting to deal with external data sources or syncs. Not as part of like a real source or sync in your workflow, but you got data flowing through here and I need to make ad hoc queries to extract data from this source to, enrich the data I'm processing. And any external system like that, database, API, et cetera, is always going to be way slower than the workflow that's processing the data. So the only way you get scalability is by being able to have lots of async requests running at the same time via like an async function. All right, if you have any more questions, I'm going to be around the rest of today and at the event tonight, the party, I guess. We have a contact form on the website. You can send me an email, and then here's the code in GitHub for what I've been talking about. So that's my talk. Thank you.
Thank you. Thank you, Ken. Other questions?
Yeah, any questions? Yes.
Hi, I'm glad you have the GitHub link. I'm curious if I were to go clone it and I have like a normal operating use of Flink, I can run it. I can make my.
You should be able to. I mean, the question is, can you just run this thing? And so we're running it in EMR, like that's our test bed, and there are instructions on the wiki page for how to run it in EMR. We typically run it against the Common Crawl data set. So Common Crawl is like this, 4 billion page data set that they're constantly updating. And I wrote a special fetcher that actually just uses the index data from there and goes and grabs files and data from S3. So that way you're not abusing all these websites when you're like tweaking your algorithm and you're not pissing off the ops team by like, whatever. So that's how we've run it mostly, is against the Common Crawl data set.
And on that, is it customizable to like would I be able to like specify a topic, say?
So there's another,
topic?
Yeah, so there's actually a second project which is like gives an example of a focused crawl where we're interested in pages written in Farsi. So that's our classifier. Like, is this page written in the Farsi language? And it was a focused crawl against the Common Crawl data set, and so you could see it finding Farsi pages, right? So that's an example of something that uses the Common Crawl code in a focused crawler. Okay.
Oh no, go ahead.
Go ahead.
So one of, I worked on a crawler before.
Mm-hmm.
Just wondering, how do you handle the scheduling part? Like, typically you would see that you have a niceness, politeness interval.
Right. So how do you handle scheduling?
Right.
Right.
You want to hit that website exactly, and would you be able to hit that with this? If not exactly, I mean, every 5 seconds.
So the current thing, so what happens is, so the question is, how do you support the politeness factor of like, I only want to make a request every 30 seconds to this website or every 5 seconds to this website. The way we do it currently is in that robots checker. It gets the robots file, it parses it. If it has a value in there, it uses it. Otherwise, it uses a default value. And when a URL comes in, it checks it against that, and it says, okay, is it time to fetch it? Like, is it okay? Great, let's pass it on through. If not, we update the status and send it back in, right, through the iteration to say, it's not time yet for this. So it really, the latency between when's the earliest you could fetch and when it actually does fetch depends on how fast we're cycling through all of the URLs, for that domain and other domains. Right. Good question. Okay, now back to you. Oh, no, here, sorry. Even get a mic.
So what's the scale, for which you ran this, like in terms of number of sites and number of pages and
So,
that
I mean,
kind of stuff?
again, at scale, we've run it against the common crawl data set,
Right.
where, with a pretty small setup, like 4 to 6 pretty beefy AWS machines, it fetched, over the course of a couple hours, with like 1 million pages, right? And that was no problem, so we're like, okay, it's going to scale up. I don't think the limitation is going to be Flink. It's going to be all that fun tuning of how many simultaneous fetchers do I have running on a given class of server, and what's the size of my pipe, out. But in theory, I love saying that. In theory, it should scale. It would be good for us to spend the money to run it, on a 50 server cluster against a full web and see what happens. Because I'm sure something would break, like it always does. So so we're not yet at that point. Actually, I'm going to ping pong back over there. Okay. Okay, go ahead. You can.
What's the AWS cost, you would say, if I were using this infra, if I were to
Well,
fetch a billion URLs?
well, if you're, okay, what's the cost to fetch 1 billion URLs? Are you fetching 1 billion URLs from the common crawl data set? Because if so, that is free in terms of the data transfer, right? It's a public data set, so it doesn't charge anything for pulling that data down. So it's just
The URLs of the actual pages?
the actual pages, because what they have is all the data stored in this WARC format, which is kind of the standard from Heritrix. And then they have separate index files that we use to figure out if something exists, and if so, where in these files. All right. Okay.
I'm interested in the score you assign the URLs to focus, so
Yep.
to speak. Is if I were to go clone the repo, is there a callback or some function?
Basically,
so I
you
can make
extend
my own?
the base parser class to implement whatever scoring you need. And if you look at there's a separate repo, which is the CC demo repo that's also public, that has an example of doing it for Farsi, right? It just runs a language classifier against it and says, okay, what is it?
Cool. Awesome. Thanks.
All right.
Any other
Any
questions?
other questions?
Oh, perfect. The timing is...
Perfect. Thank you very much, Ken.
All right, thank you. All right.
Yeah.